Sorry for the delay, guys, and thanks for coming over to this presentation. Hope you will be happy about visiting this talk, because today we are going to discuss capabilities of Ignite that are relevant for data scientists and researchers. So those guys who want to deploy their data sets in a distributed cluster and to apply different calculations, develop different algorithms using not just simple queries, but something more advanced that will help you to get more details, bring more benefits from the data sets you have in your distributed cluster of machines. And before we start with this, a couple of words about myself. My name is Denis Magda. I am Apache Ignite PMC chair. Those who are not familiar with Apache Software Foundation, for you I will say that every kind of top level, every project that belongs to Apache Software Foundation has a PMC, a Project Management Committee. And that Project Management Committee consists of the folks who contributed a lot into a specific project. And here we also have the same Project Management Committee for Ignite, and presently I am leading this committee, but I don't have any privileges. I'm just doing all the dirty paperwork and resolve any issues that may arise during the lifetime of our Apache Ignite community. At the same time, I work for GridGain that builds enterprise level solutions on top of Ignite. And presently, I'm taking a role of Director of Product Management. But I joined that company as a software engineer, and I helped a lot Ignite and GridGain users to deploy both products in production. And this is why you can expect to get from me a lot of different technical details and architectural information we deployed and embedded into the product we are going to talk about today. So, and if to speak about the use cases for data, for our analytical use cases, for data scientists-based use cases, I would propose this agenda. So first, before we start with components overview, we want to see what are the use cases that are already being implemented and provided on top of Apache Ignite. After that, I'm going to walk through several components, main features and main capabilities that are needed to you as a data scientist or data researcher. So such functionality as a data grid that is needed to store and process a massive amount of data. Then we are going to speak a bit about the memory architecture that is implemented in Apache Ignite, and we call it durable memory architecture. And finally, I'm going to cover some of the APIs that are used not only by application developers who work for financial systems or who develop different web services, but also the APIs that are needed for data scientists, such as SQL, such as Compute Grid, and different machine learning capabilities. And throughout this, I built this talk as a sort of workshop, but the only difference is that you're not going to play with the code right now. I'm rather going to, for every component I'm going to show, for every functionality I'm going to present, I'll show how to start with it by running several simple demos. So, but before we move on with machine learning APIs and data and APIs needed for data scientists, I want to give you a high-level overview of Apache Ignite. So first, Apache Ignite is a distributed database and computational platform. All the data that you have in Ignite can be stored in your memory-centric storage. Memory-centric storage means that your RAM, your random access memory, is treated as a full-fledged storage tier for your data and indexes. And this is how you can gain in-memory performance benefits from your Apache Ignite deployments. At the same time, all we know that memory is not enough for mission-critical applications. We want to persist our data. And if you want to get the durability characteristic for your Apache Ignite-based deployment, then you need to enable persistence. And here is you have two options. So first, you might use Ignite native persistence that is available in the most recent Apache Ignite versions. And that persistence is natively integrated with the overall memory architecture. And in short, it allows you running SQL queries over the data that is both on disk and on RAM. It allows you to leverage from instantaneous cluster restarts, meaning that if by some reason whole your cluster goes down, you don't need to warm up all your data in RAM after the restart. You can activate your applications, and the applications will run your queries over the data that is on disk only. And in parallel, you can warm up your memory, your RAM, to get better performance. And in the same time, you can use some third-party databases here, like Oracle, MySQL, Cassandra, or MongoDB. And here is for sure some differences and limitations, and we can discuss them during the QA session. But anyway, on top of this memory-centric storage, you can use a variety of different APIs. And some of these APIs are useful for data scientists, and we are going to look into them, such as SQL, such as compute, and machine learning. Speaking about Apache Ignite users. So Apache Ignite is used in a variety of different realms and markets. It's used for different applications and use cases. But what I'm interested in today is this specific realm, like healthcare and medicine. I do know, as an Apache Ignite PMC chair, I know that there are at least two companies that use Apache Ignite for different scientific-based projects. And one of them is the company called eTherapeutics. What the company does, what the company did. Actually, the company takes a series of different proteins, and they can analyze those proteins to reveal different diseases. And all the proteins, as you know, they consist of millions and billions of cells. And by analyzing those proteins, they can find out, they can spot specific cells that can trigger different diseases. And knowing these cells, they can come up with different treatment or different drugs that can be prescribed to you, and so that you can get rid of a disease you have. For sure, it was impossible for this company to do this analysis in a parallelized way, because all the data was stored in some relational database, and they had to execute all the queries in a batching mode. And this is how they could not, gain a lot of benefits from this architecture. And they started looking in different in-memory-based solutions. And this is how they came to Ignite at some point of time. And finally, what they did, they deployed a cluster of Ignite machines and preloaded all the samples, all the data they have at that time, and they could parallelize all their calculations across a cluster of machines. And by doing this, they achieved 80% X performance improvements just by doing different calculations over the data that is stored on your server nodes. And even more, once they migrated to this distributed architecture, they freed up a lot of resources so that the whole cluster was underloaded. And after that, the cluster, a lot of scientists and researchers who work at this company, they could get access to this cluster and execute and check different calculations and execute different research methods that were in their that were waiting for some resources for a long time ago. Okay, so and now let's suppose we decided to use Ignite as our distributed storage and computational engine for our research project. And here is first we want to know how the data is being distributed. How can we really parallelize all the queries execution and computation processing in our cluster? First, all the data we have, it will be distributed across a cluster of machines we have. Like if you have 3 machines, like it's shown on this picture, then a subset of the data will be located on one node, and the other node will be responsible for another subset of the data you have. This is how you achieve the distribution. Let's say that my account or my record will be located in this machine, while the record of any of you will be located on other machine. And when you start working with this data, a lot of the queries can be directed directly to the nodes that own a specific data set. Next, once the data gets to a specific cluster node, we need to store it somewhere. We need to store it in memory. And every cluster node runs so-called durable memory. It's based on so-called durable memory architecture. The durable memory architecture implies that first, RAM, your main memory, is going to be used as your primary memory tier. And then if you want to have the durability for your system, or you cannot fit all the data in RAM, you need to enable the disk tier. The RAM tier, the memory tier, is based on heap implementation. Ignite is a Java product, and kind of 95% of all the code is written in Java. But at the same time, when it comes to the memory storage, all the data resides in manageable memory. The memory that is not visible to garbage collection, which allows you to store as much data as you can directly in RAM and not worry about long garbage collection pauses that might happen with a variety of applications that can try to fit everything in the Java heap. At the same time, if to speak about the native persistence layer, if you cannot fit all the data in RAM, which is mostly the case for research projects, then you can store all the data on disk, and a subset of the data will be located in RAM, depending on the resources you have. And this is truly allows you to have both benefits of many systems we have. Like you will have the durability of disk that is usually provided by NoSQL or relational databases. And at the same time, for the hard data, you will get the memory performance. Okay, now let's quickly look how we can start our cluster on my local laptop. I'm going to use it, so Joe, for the sake of performance, okay, I'm going to use a command line interface. Let me scale it out. Okay, so here is I have Apache Ignite version 2.3 that is going to be released in the nearest time. And we want to start the first cluster node using this command and this configuration. The configuration simply sets up different networking related parameters so that all my cluster nodes can find each other on my local machine. And I want to start one more node. Yeah, I had to restart my laptop, so now I have to type out all the commands once again. Okay, while this is being studied, so here we see that the first node is almost up and running. While this happens, I want to connect to my local cluster from a monitoring tool. To do that, I need to start a special intermediate application called Apache Ignite Web Agent. So the web agent, it's a sort of a mediator between your cluster and the web interface I'm going to show to you. So this web interface is located here. That's Apache Ignite Web Console, and I'm going to use the version of console deployed hosted by GridGain, so you can also play with it if you want. But once you decide to go to production, you can take and deploy this console on your own in your own environment. Okay, here is what we see. I could connect to the cluster. I see 2 server nodes up and running, and here is also you can find some other information, system-related information such as CPU usage, heap usage, and other metrics related to the data that is stored in the cluster. We don't have any data for now. Let's try to start the first simple application that will try to put something into our distributed database. And then let's try to read this data. To achieve this, let me first increase this font size. Okay, now it's better. I'm going to use basic examples that are delivered with every Apache Ignite distribution. And the first one is the simplest. Like I explained that by default, all the data is partitioned, distributed across all the machines you have in your cluster. It will be distributed evenly so that all the workloads can be distributed in the same way. And once you start using key value APIs, actually key value APIs is the fastest way possible to get a single key or update a single record stored in your Apache Ignite cluster. Simply because we can take your key, and once we know this key, we can calculate a destination node. And this operation can be completed in a constant time, regardless of the size of the data you store in your cluster and regardless of the size of your cluster itself. Okay, so here is we are starting this simple application. What this application does, it just connects to our cluster using the same configuration. And then we are going to put some data into the cache. Cache notion, so when you hear cache in Ignite means the same as a table in the relational world. Like this is actually the data structure where we store all your data sets. And on top of this data structure, as you will find out later, we can build SQL schema, we can build indexes around it, or on top of this data, we can run not only simple key value computations, but you can develop and run your more advanced calculations. Okay, this example is over, and here as we see that we just could get some data from the cluster and put some data in the cluster. Nothing impressive. This is just simple. This is how you can start with your first cluster on your local laptop and do some useful work with it. Going back to our presentation. Persistence. A couple of a bit more words about our persistence. So the persistence in Ignite, if to speak about Ignite native persistence, it operates in a way similar to the disk-based databases. Like when you update, here is we have some, let's imagine we have some data node. And once an update arrives from your application, first this update will be written to memory, to RAM. And right after that, that update will be persistent, appended to the write-ahead log file. That's a kind of a familiar notion, right? So every disk-based database, I think, or at least most of the databases, they maintain so-called write-ahead log file. And once this happens, your application will get an acknowledgement, and it can keep executing the rest of the logic is developed in it. But then write-ahead log file is not ideal for the situations when you want to get when you want to get instantaneous cluster restarts, and meaning that you want to avoid RAM, your memory warm up after the restart. And also, write-ahead log doesn't allow us to execute, let's say, SQL queries if not all the data is in memory. And to support both SQL over disk and to support instantaneous restarts, we checkpoint all the data that was updated in memory to special partition files on disk. Like all the data you have in the cluster is located in partitions or shards. And for every shard or for every partition, we have a dedicated file on disk. And then all the time, when you update your data in RAM, the data will be checkpointed to this partition files in background. Next, once you preload all your data into the cluster, and once you start using it for your research project, at some point of time you might need to use some, and you might need to have more advanced queries rather than standard key value APIs I showed you. And SQL language is probably the most advanced and widely used language for advanced queries execution. And Ignite can be fully used as a distributed SQL database, meaning that even if at some point of time you decided to use only key value or compute operations in your cluster, at some point of time you can easily enable SQL capabilities in Ignite, defining a SQL schema on top of the data you have, and you can run all the well-known select, update, delete, insert statements. You can define indexes, you can drop indexes, you can define additional schemas or drop schemas in real time without any cluster restart. So that's not required. And you can connect to your cluster not only from Java, C++, or .NET applications that have special Ignite libraries developed for them, but also you can connect to your cluster by means of ODBC or GDBC drivers from your favorite programming language like Python or Ruby, or from any tool you like, or any tool you use, like Tableau, for instance. Let's take a look at a quick example on how we can use SQL capabilities of Ignite. Here I still have the same cluster of 2 nodes running on my local laptop. And now I want to connect to this cluster from using special command line tool called SQL Line. This tool is developed, it's available in open source, and presently we use this tool for Apache Ignite connectivity from a terminal window like this one. Okay, so here is, I should have somewhere this connection string. Let me try to find it. SQL line. Okay, so we can even do it simply. I can go quickly to the Apache Ignite SQL documentation and find out this connection string SQL line. Here is, we have it. Okay, now we are connected to the cluster. And next step would be, I want to execute a simple SQL script. I should have this script somewhere over here. Yes, here it is. Let me show it to you. So basically what we are going to do, we are going to create 2 SQL schemas and 2 caches and 2 SQL schemas in my cluster. The first will be city, where we are going to have, every city will have only ID and name. ID will be our primary key, and also there will be persons who live in this city. Then I want to define some indexes, and I want to fill out these caches and tables with some sample data. Pretty simple. So to do this from this SQL line tool, I just need to execute the script. Okay, everything is ready. Let's go to the web console. Okay, here is I see, yes, I have, once we executed this create table command, two things will happen. First, Ignite will create a distributed cache for you. That's actually your kind of your storage, your data storage, where all the entries will be placed in. And also on top of that, we define SQL schema. We are going to maintain indexes for you. We are going to solve all the mappings from insert commands to actual commands that will be executed in Apache Ignite cluster. So let's quickly run several examples. You can execute joins over your data. You can execute simple update operation, like for this city. We updated this value, and now we want to see that the value was updated. This happened. And the same is true for delete operations. If you want to delete the value, you can use not only key value APIs, but you also can rely on SQL. So we no longer have that city in our distributed cluster. Okay, that's about SQL. What else might we need? What else might a data scientist need for his use cases? Compute grid. So all these key value operations, all these SQL-based APIs, they do one thing that you might avoid in for some of the scenarios. They send a request to your server nodes and they bring the data back to your applications. Which means that if you need to iterate over a huge amount of data stored in your cluster, then if you run a key value call or if you run an SQL query, then you're going to move the data from your cluster over the network to your applications. This is how you're going to saturate your data. And this is how, but there are options how you can avoid this. To avoid this, you can use so-called compute grid, which means that instead of sending queries to your server nodes that will give you data back, you can send calculations to your server nodes, and all those calculations will be executed directly where the data is. Like it's shown in this picture. Here is we assume that your application developed some computation, like a standard computation. For instance, we want to, let's say that we have a database of cities and people stored in our cluster, and we know that some blizzard is coming to New York, and we want to notify all the New Yorkers that that's going to happen in a couple of days. We want just to send them a special text message. And you can write this logic on your application side and send this logic to all the nodes where the New Yorkers are stored. And this logic will be executed over the data set that is presented on these machines, and the text message will be sent to all the people who live in New York. And what you get with this scenario is that you avoid data movement. You don't need to bring all the records of people who live in New York to your application. You just can send a computation to the place where the data is. So actually, compute grid in Ignite is a sort of a MapReduce framework or fork join framework. The principle it works is pretty simple, and it's the same as with Hadoop MapReduce engine. You just take a computation, and this computation, depending on the logic you have, it can be split into several subtasks or jobs, and the jobs will be executed across the machines you have. This is specifically interesting and useful for data scientists who store massive amount of data across a cluster of machines, and when they need to execute some algorithm or logic, they just can code this algorithm and logic and send it as a computation to the cluster of nodes. And actually this is exactly shown here is on this slide, but from a different view. For instance, when you use SQL or key value APIs, this is what you get. Your client application sends some request and you bring the data back to your application, and then you do all the processing on the application side. But with the compute grid, you achieve so-called collocated processing. When a computation is sent instead to your server nodes, to the node that store your data sets, and it's executed there directly. Okay, let's quickly show how you can do a computation like that in Apache Ignite. Here we have a simple compute application. So what it does again, we are connecting to the cluster. Here we have a simple demo. We have a string that consists of 4 words. We want to split all these words and calculate the length of every word across all the machines we have. This is how we want to distribute the workload. So once this calculation is started, it will be sent for the execution to these nodes and to my local node 2. Okay, so that was calculated. Here as we can see that a part of the string was calculated on this local node, on this application side too. But also you can see that this overall computation was partially executed on the other node's side using their resources, like this node and that node. Furthermore, these nodes, 2 nodes that are running from my console, they do not have class implementation of this computation locally, meaning that there is no any logic class definition in their class path. And once I, as a data scientist, decide to update this computation, probably I want to fix a bug or I want to introduce some new parameter to my computations, I do not need to restart my cluster with the data. What I can do, I just can go ahead and update all the data here directly. For instance, let's type something like that. If word length is bigger than 2, I want to print out some message. And otherwise, I'll print out a different message. Again, and now I'm restarting this application. The implementation of this computation was changed. The class was updated too. But at the same time, we don't need to restart my server nodes. Because Ignite has a special capability called peer class loading, peer deployment, meaning that when these 2 server nodes receive this new computation for the execution, they will find out that the version of the class was changed on the application side, and the nodes will preload the class, bytecode of the class over the network, and will deserialize this computation to the new version. And now, okay, and here as we can see the result. Here as you can see this output. That was a part of our updated version of our computation. So the upshot is that once you deployed your cluster of machines and preloaded all the data you need there, you don't need to restart your cluster just if you need to update a calculation or SQL query or key value API. Everything can be done in the way that the cluster will be up and the server nodes with the data will be up and running all the times, and you need to restart only your application logic, your applications deployed somewhere. Finally, why we are talking about data grid, compute grid, and SQL capabilities in Ignite? Why are they so relevant for data scientists? Actually, if you use data grid and compute grid APIs in Ignite, you already can start building all the complex algorithms or calculations you need for your specific use case. You don't need to have any machine learning framework on top to achieve this. If you're kind of experienced enough, all you need to do is just take compute grid, data grid, and implement everything on top. For instance, there is one of the side projects, some so-called genetic algorithm grid, that is being developed outside of Ignite, but basing on data grid and compute grid capabilities of the platform. And what this grid does, what this framework does, it can use biological population as a method for your problem solving, like in robotics, in different machine automations, in financial realm. So the idea is simple. You need to store in your cluster a set of chromosomes and genes, and every chromosome represents a specific solution for your use case. If you are satisfied with this chromosome, it means that you find an optimal solution, let's say, for your logistic application. At the same time, if you're not happy about it, you can do so-called fitness calculation or crossover or different mutations by taking different chromosomes, extracting genes from them with characteristics you need, and derive new populations of chromosomes based on the samples you already have. And all this is done with the usage of data grid and compute grid functionality. If you take a look at this block, you will find out that actually all these fitness calculation or mutations, they are implemented in the form of compute grid calculations. Kind of, I showed you how you can quickly calculate the total length of a string by writing a simple Java logic. But for sure you can do more. You can build a genetic algorithm based on compute grid, and that's kind of a proof of that's feasible and possible to achieve with Ignite. And finally, so using the same data grid and compute capabilities, Apache Ignite community decided to to simplify, to facilitate a lot of data scientists and researchers developing its own machine learning framework on top of Apache Ignite data storage. So in the first step, the community released so-called distributed core algebra, which means that now you have all the vectorized calculations, all the matrices-based data structures developed and available for you as a part of Ignite. Next, on top of this distributed core algebra, the community started developing a variety of well-known algorithms needed for machine learning, such as k-means clustering or linear regression, and such as decision trees, for instance. This framework presently is available in the beta state. So here is an Apache Ignite PMC. I'll encourage you to try it on, to give us a feedback. And also, if you're kind of interested or if you crave for developing a distributed version of some machine learning algorithm, you are welcome to our community. So we are a supportive community, we are a responsive community, so you can come to us and propose a development of some algorithm that is, for instance, presently missing in Apache Ignite. And that will become a part of this machine learning grid component we are working on right now. And the final sample I just want to show you is related to machine learning APIs. For instance, here is again, we have the same cluster, and among the samples we have in Ignite, you can find, for instance, an example of linear regression. So here is we're going to connect to our cluster to preload this sample data set and then to do some standard calculations using the linear regression implementation in Ignite. Okay, let's do it quickly. I just want to show you that we're not going to look into it because we are running out of time. But anyway, so there are much more samples that I showed you today. So you're welcome to download the project and to play with it. And I hope that I could show you that actually it's pretty simple to start with Ignite, right? So during this short presentation, you could see that you as a developer, you as a data scientist, you just can start your cluster on your local laptop in a matter of minutes. You can preload the data there quickly. And then you can start exploiting using your cluster with key value, SQL, and machine learning APIs. So it's it's up to your imagination, it's up to your business needs, and Ignite for sure can provide you with a variety of functionality that you can use for your specific use case. So having said this, I am ready for your questions. Mm-hmm.
So is it gonna, if it's synchronous, right, to the disk, so that means it's gonna add some latency, right?
Mm-hmm.
So I'm just curious, like, are you only just simply when someone, let's say if you update the data in the cache, are you really only persisting the write-ahead log to the disk, or you're also at the same time exact same data that you have in the memory, you're also maintaining that on the file synchronously?
No, actually, we write this update to the write-ahead log file only. Like it's shown here is, like, let's say that even if you have the strongest full synchronization mode,
yep.
And when your application updates some data, first it will be updated in memory, appended to the write-ahead log file, and that's it. After that, your application will get a kind of a response, and you can execute the rest of the updates you have or the rest of the queries you have. So your applications starting since that point of time, your application will not be blocked by this operation. And then over the time, depending on different factors, we are going to write to sync updated pages directly to the partition files on disk. It depends on different parameters like frequency, update frequency, or depends on how much, what's the fraction of dirty pages we have in RAM. A dirty page is a kind of a page that was updated in RAM, but was not synced to disk.
But I guess the question is, if let's say that during that time when acknowledge number 3 is done, but the number 4 is not done, and your cluster goes down, when it comes up,
Mm-hmm. We need to reapply all the data that is in the write-ahead log file. So that will be, so it means that your kind of the time of your cluster restart, the time of your downtime is driven by probably the size of your write-ahead log file. But it means that if kind of the checkpointing kind of happens constantly, it means that most likely if kind of some disaster happens and the whole cluster is down, only a small fraction of the write-ahead log file will not be written to the partition files, which means that once you restart your cluster, you're quickly replaying a remainder of write-ahead log file, and you are good to start executing your SQL, like all your applications that, for instance, use SQL queries. Because we don't need to wait while the data is preloaded from these partition files to memory. That's not needed. All the queries can be executed directly over this data.
Got it. So you might have a stale data for some time.
Mm-hmm. It's not stale, it's just it's not in memory. So you will have kind of lower performance because all the data is on disk, but
yeah, I guess what I meant is like if the cluster goes down and write-ahead log is not applied yet, then you might have a stale data during that time.
No, you will not have. You will have it in the partition files. But means that once we copy data from here, but from your application standpoint of view, you will never have any stale data. It will be stale at the level of partition files, but globally at the application level, you will not have any stale data because all this stuff is synchronized internally by Ignite.
The pure class loading is a very powerful feature, but
Not. No. Probably you just need to be sure that that logic is written so that you test this logic, like so that no any developer executes malicious code that can do something bad with your cluster. If you do all this basic testing stuff on your side, then you're good to use computations.
Why do you even allow it to be turned off? It seems like it's so powerful.
It's just because of historical reasons. Because before that functionality was in Ignite probably 1.0, it was possible to preload classes of your objects stored in the cache. But once we developed our new serializer, which is called binary marshaller, you don't need this because we don't need to deserialize data on the server sides when you execute different queries, and that functionality, and we removed all the peer class loading capabilities for the objects that are stored in your cluster. This is what we did. But and was enabled at that time only because if to imagine that a version of that object stored in a cache is updated, then we would be remove all the previous data from the cache and update it to the new version. It was a kind of long operation, and this is why the parameter was disabled by default. Yeah.
On this here, if I had a backup copy, so I've got two versions, when do I get my back? Do I get it after the first one or after both of them?
It depends. If you use the full sync mode, the strongest synchronization mode, your application will get the egg only when a primary and a backup copy replies. But you can use so-called primary synchronization mode, meaning that once the primary replies, your application is good to go.
For native systems, any limitations for the type of the hard drive? Do you support regular hard drives or only flash SSDs?
We use Java file system APIs. So everything that can be mounted as a file, as a file system, that's what we support. And this the same way we can work right now. The same way we can work with Intel 3D crosspoint technology. If you can mount it as a disk drive, you can also use Intel 3D crosspoint for your persistence layer. Mm-hmm.
So going back to the PR class loading, in my experience, what you showed was just, and I could be wrong, so please correct me. What you showed was just pure Java code, which was already in your class pack. But when I have my compute jobs, which say I have a class which is my application class, and there's some slightly complex business logic instead of just summoning an application, then I've noticed that I have to have that class in the class path of my Ignite node customers.
Why?
Because it then complains that it cannot find a new definition for my class. So for example, what you showed was just pure Java, right? But what if I have my business logic to say class person, right? And I have business logic to say calculate the height of the person.
If this person is stored in the cache, like
No, it's not stored in the cache, it's just pure Java code.
okay, then I can show this quickly. So yeah, anyway, we ran out of time, guys. And if there is someone else who wants to ask questions, you can stay here. If you need to go, I'm not going to strand you here anyway. I just give me 1 minute. So let's say that you're talking about this use case. Let's say I have a simple class, да? Private static class, custom class, and I have some field, let's say age, and I want to initialize it to some value. Okay. So you are talking about this case. Now you want to use this class, right?
Yeah.
In your logic. Okay, I want to create an instance of this class. And setting 45 years. And now I want to print out this H. So here is two things should happen. Let me start it first. First, again, my server nodes that are still up and running, they're going to see that the class version was changed again, so that they will reload it. And once the class version is reloaded, the object will be instantiated, and the service will start executing this logic. Once the server comes to this point, it will check its local class path. It will not find this class locally, and it will send a query to my application requesting this class. And this class will be preloaded over the wire again. Let's check it up. Here it is. So this happened. It was preloaded.
Is this something version change? Like I was testing this on version 1.1.
I don't know. No. It was supported. It was supported for a long time. Probably you hit some bug. Just send the message to the user list, and just providing your sample. Just, yeah.
This would work similarly with external frameworks and libraries that the program is using in Java.
Here is my recommendation. It's a good question. So should we kind of what to do if you use, let's say, some third-party libraries like Spring Framework? Here is my recommendation would be if you're not going to change a version of the library for a long time, it's better to add it to the class path of your server nodes, because some of the libraries they disallow data serialization and deserialization. For instance, we hit this issue for some of the for some of the frameworks. So just put big frameworks to the class path, but as for your logic, just write it this way.
So in one of the slides you had the C equal to C1 plus C2, right? Where you move the code to the place where the data lives and you do the computation.
This one.
Yeah. So what if the C1 and C2 are in two different nodes? Where does your computation run? Does it run in the node where C1 is residing, or I mean C2?
Here is it's a good question. So what happens where the computation executed, right? So first, there are two phases. First is map phase, and the second is reduce phase. Even if you take this simplest computation here that takes a string as an input parameter and splits the string into 4 sentences, and then for every sentence we execute a subtask or job. We call it job. This application knows the state of your cluster. It knows that there are 2 server nodes running. And it will take, let's say, one subtask that should calculate a length of count. It will be sent to one node, while the other subtask will be sent to another node, like it's shown on this slide. And once all these nodes are done with their calculations, your application will receive result sets if it's needed. Like here is we are sending back lengths for every, and it will be aggregated locally on your application side.
The logic runs in the application.
Map logic and reduce logic. Map and reduce. Like when you need to take the final result set, like here is all this logic was calculated across all the cluster nodes I have for different sentences. But then when everything was done, I got a length for every word, and I aggregated a final result set on this local application.
This example here, when the compute.all is executed, are there actually 4 separate classes that get sent to it, or one class that gets sent to it?
Actually, no. So here is we are sending only this anonymous class.
Yeah, but you add that anonymous class 4 times to the list, and you send your call, assuming there's 7 objects. So how does it know they're all the same class? Or does it know they're all the same class?
Here is what we did. So it's a special type of API. So by default, you can just create your single task that will be split into several jobs. There are different techniques how you can write your logic using compute grid. But here is what we're doing. Here is we're preparing a list of different computations, and there will be 4 computations in total. We put all these computations, all this sort of meta information into this list, and then we send the list this way. We need to take ignite, reference to compute grid, and execute this method. Once all the data, all the computations are spread out and calculated remotely, we will get the results stored in this collection. And here is locally we are iterating over the result.
So I understand all those mechanics. So my question was specifically the calls array. Is that 4 different classes? It's got 4
No.
What is each element?
I see a point. So now, by default, you mean that are we going to preload the classes 4 times, right?
Yeah.
No, we are not. We are not. So once there are different kind of deployment options. Like by default, if this class already available, a class of this version is already available on a node, then it will not reload it all the times. It will load it only once. And then when you're going to send the same computation to this node, it will use the same class that it preloaded long time ago. And you can run multiple computations of the same type in parallel on this node. They all are going to reuse the same version preloaded long time before. But then also what's important to note here, once you decide, let's imagine that this computation was used in different applications, and then in one application you move to the next version of this computation. And now you have 2 applications running in parallel that execute the same calculation but of different version. And still Ignite can support multi versions on the same cluster node, saying that if one application uses this version of the class, okay, we are going to use that class version. For the rest of the computations, we are going to use the next version of the class. Make sense?
Question, so for peer class loading, is there an issue with lambdas? I only use class version.
Yeah, it's supported for, yeah. If you are on Java 8, yes, you can use it.
Okay. And does it have to be serializable in all these, the classes? You just mentioned the serial version ID stuff, right? So if I use a class that's serialized into a serializable, if I assign a serial version, ID,
Uh-huh.
then if I don't change it,
Yeah,
then it won't load that class.
yes,
Right? So if I change my
yes,
logic, it'll fail, right?
that's true.
Right. The other question I have is that in the compute, can I access keys within that cluster? Or does that,
Yes, you can. So like if you, the same way.
will that be co-located with the keys?
Yeah, if you want to run a kind of a collocated task, you need to use, if you want to collocate your computation with your data, you need to use a special API called Ignite Compute Affinity Run or Affinity Call. Here is what you're doing. You are passing a key, like some unique key you want to collocate the computation with. And then inside of your computation logic, you can access caches. You can,
Specify the key. In my,
yeah. And this computation will be sent. This like the key you pass here. Okay, so like this key that I passed here, that will define a destination node for my calculation. If you know that all the data that you're going to access from your computation is located on the same node where this key is, then you did this. Ignite will just send this computation exactly to that node that owns this key.
So with all the versions of your classes, do you have a way to clean them up? Are they stored permanently, or do they kind of expire?
So when all the applications that use this class are down, then the class will be removed, purged from the node memory.
These are client node or
Client node, like client node, like client application. When, like here is every time when we were restarting this specific application, my server nodes would go and remove the class from their special remote class loader. Okay. If you have any other questions, stop by. Thanks.